Let's talk about classification, the logistic regression algorithm in particular. Regression and classification are both supervised learning techniques, thus share a goal of modeling some outcome variable y by predictors x. But where they differ is in the structure of y. When y is quantitative, this is a regression task. And when y is categorical, it's a classification task. For example, we might want to model y, whether or not somebody voted in the previous election, by predictors such as their age, party identification, and so on. Or the engineers of self-driving cars need to model y, whether a detected object is a human, car, or bike, based on the object's speed, shape, etc. So why do we call this a classification model and not, say, a categorical model? The reason is that in machine learning, we'll often use these models to classify y. That is, given a set of predictor values x, we can identify the most likely class or category of y. And in order to determine what categories are more likely than others, we need to utilize some measure of uncertainty. In general, the occurrence of a given event ranges from impossible to certain. At the tipping point between these extremes are events that are equally likely to happen or not happen. We can quantify this spectrum using probability. Probabilities fall on a scale from 0, impossible, to 1, certain, though most events fall somewhere in between. For example, if we flip a fair coin, the probability of getting tails is 1/2. We're equally likely to flip tails or not. If we roll a fair 6-sided die, there's a 4 out of 6 chance that we observe a value of 4 or under. Similarly, there's a 2 out of 6 chance that we roll a 5 or 6. But probability isn't the only way to measure uncertainty. Odds compare the probability that an event does occur, p, to the probability that it does not occur, 1 minus p. Rearranging this formula, we can also calculate probability from odds, as odds over odds plus 1. Consider an example. The odds of flipping tails compares the probability that this event occurs, 0.5, to the probability that it doesn't, also 0.5. Since this event is equally likely to happen or not, the odds of this event are 1, or people often say 1-to-1 odds. Similarly, in our dice roll, there are 2-to-1 odds of rolling a 4 or under. That is, we're twice as likely to observe a 4 or under than to not. On the flip side, this means that the odds of rolling a 5 or 6 are 1-to-2. That is, we're half as likely to observe a 5 or 6 than to not. Note that, though probability and odds both provide the exact same information, it's on different scales. Whereas probabilities can only range from 0 to 1, odds can be any value at or above 0. The odds of an impossible event are 0, the odds of a certain event are infinite, and the tipping point occurs at 1. Though it might not seem useful yet, we can also measure uncertainty on the log odds scale, where log refers to the natural log, ln. In our examples, the log odds of flipping tails are 0, the log odds of rolling a 4 or under are roughly 0.7, and the log odds of rolling a 5 or 6 are roughly negative 0.7. The main thing to notice here is that the log odds gives us the same information as odds and probability, but again, on a different scale. Whereas probabilities fall between 0 and 1, and odds must be non-negative, log odds range from negative to positive infinity with a tipping point at 0. Focusing just on this tipping point, if an event is equally likely to happen or not happen, it has a probability of 0.5, odds of 1, and log odds of 0. In this video, we'll explore how to incorporate these ideas into logistic regression, a common classification algorithm for modeling a binary or 2-category outcome variable y. Consider an example. Suppose we want to forecast whether or not it will rain tomorrow in Sydney, based on today's 9 a.m. humidity level. Let's check out some sample data. From the left plot, notice that on days without rain, the humidity hovers around 65%. On days with rain, humidity tends to be higher, hovering around 90%. The right-hand plot shows this same data, but it plots the binary 0-1 rain outcomes on the y-axis versus humidities on the x. Now, since we've essentially converted rain to a quantitative 0-1 dummy variable, your first instinct might be to model rain by humidity using our usual linear regression tools. But there's a problem. Whereas rain outcomes y can only be 0 or 1, nothing in between, this model assumes that y can fall anywhere along this line. It would therefore give nonsensical predictions. So instead of trying to model these 0-1 outcomes, our next instinct might be to model the probability of rain. But this too has a problem. Whereas the linear model extends from negative to positive infinity, probabilities must be between 0 and 1. So again, the model could give nonsensical predictions. For example, it might give predictions of probabilities that are either negative or exceed 1. So what would happen if we model odds of rain on any given day? Well, the same story. This too would be nonsensical. Linear models can extend from negative to positive infinity, whereas odds are restricted to be non-negative. So this is where the log comes in. Since, like our model, the log odds of rain can range from negative to positive infinity, modeling rain by humidity on the log odds scale does not violate any mathematical properties. Using log odds might seem strange, so let's convince ourselves that it can be useful. First, let's model the log odds of rain by humidity. This model is represented by the familiar equation for a line. The positive slope indicates that the log odds, hence certainty of rain, increases as humidity increases. Further, the dashed line at 0 indicates the tipping point in the log odds, or where rain becomes more likely than not. Specifically, the log odds line surpasses 0 at roughly 90% humidity. Thus, when humidity exceeds 90%, rain is more likely than not. However, it's tough to interpret much more since the log odds scale is a little bit unintuitive. But this isn't a problem. We can transform this model from the log odds scale to the friendlier odds scale by taking e to the log odds. When we make this transition, we no longer have an equation for a line. Rather, we have an equation for an exponential curve which respects the fact that odds can never go below 0. This presents the same information as the log odds model, but again on a different scale that's easier to interpret. For example, note that when humidity level is roughly 90% again, the odds of rain are roughly 1 to 1. And when there's nearly 100% humidity, the odds of rain are roughly 2 to 1. That is, rain is roughly twice as likely than not. We can go one step further, transforming the model from the odds scale to the probability scale by remembering that probability can be calculated by dividing odds by odds plus 1. This model is again a curve, and if we zoom out, we notice that this curve is constrained to be between 0 and 1. That is, we've successfully built a model which makes sense, or basically it doesn't violate the properties of probability. Not only this, but the probability model is easier to interpret than the log odds. When humidity is around 0%, there's near 0% chance of rain. When humidity is around 90%, there's a roughly 50% chance of rain. Just as in regression settings, we can use our models to anticipate the value of an outcome variable at different predictor values. For example, suppose there's 95% humidity at 9 a.m. today. Plugging 95 into our three equations, we determine that the log odds of rain tomorrow is roughly 0.412. Thus, the odds of rain are roughly 1.5. That is, rain is roughly 1.5 times more likely than not. Accordingly, there's a roughly 60% chance or probability of rain. We now have the same information on three different scales, and all agree that rain is relatively likely. Further, just as in regression settings, we can interpret the coefficients of our logistic regression model. Let's first consider the model on the log odds scale. Again, this is represented by a line with a slope of 0.06. Thus, we can interpret this to mean that for every 1 percentage point increase in humidity, the log odds of rain increase by roughly 0.06. Since a 1 percentage point increase isn't very meaningful in the context of humidity, let's consider a 10 percentage point increase in humidity. Multiplying the slope by 10, we can conclude that for every 10 percentage point increase in humidity, the log odds of rain increase by roughly 0.6. To emphasize, there's a 0.6 increase in the log odds of rain for any 10-point increase in humidity, whether from 30% to 40% humidity or from 60 to 70% humidity. Since the log odds scale, again, is a bit counterintuitive or unintuitive, this coefficient interpretation is also kind of confusing. So let's consider the model of the odds scale. Importantly, since the odds model is not linear, we can't interpret the humidity coefficient as a slope. Mainly, the rate of increase in odds as humidity increases is not constant. This rate is slow when humidity is lower and more rapid when humidity is high. With this in mind, the coefficient on the odds scale tells us about the multiplicative change in odds when we multiply humidity or when we increase humidity by 1. To calculate this multiplicative change, we can exponentiate the humidity coefficient. The result is 1.064. Specifically, for every 1 percentage point increase in humidity, the odds of rain multiply by 1.064. Let's consider this for a more meaningful 10% increase or 10-point increase in humidity. Multiplying the original coefficient by 10, then exponentiating, returns a value of 1.87. Thus, for every 10 percentage point increase in humidity, the odds of rain multiply by 1.87. That is, the odds nearly double. For example, the odds of rain when there's 100% humidity are roughly double those when there's 90% humidity. Similarly, the odds of rain when there's 70% humidity are nearly double those when there's 60% humidity. In general, though the absolute change in odds is not constant, the multiplicative change in odds is. Finally, and unfortunately, though it would be nice, we can't really interpret the humidity coefficient on the probability scale. First, since the probability model isn't linear, the rate of change in probability with humidity is not constant. Not only that, notice that the multiplicative rate of change in probability with humidity isn't even constant. For example, the rate of increase in probability is slow when humidity is low, then higher when humidity is between, say, 60 and 90 degrees, but then it's slow again. In conclusion, we've built a logistic regression model for a binary categorical response variable. The slide here provides a summary for future reference.